Okay, in this lecture, we're going to keep moving through the section 1.6 material on applications of linear systems. And here we'll look at the application of balancing chemical equations. So in general, chemical equations describe the quantities of substances which are consumed or produced by a given chemical reaction. And so as an example of one chemical equation, let's look at the following. So let's suppose that we have propane gas, which is burning. So we would have propane, C3H8, combining with oxygen, O2, in order to form carbon dioxide, CO2, and water, H2O, and this chemical reaction would be described by an equation of the following form. So here we have our two reactants, propane and oxygen, which are combining or reacting to produce carbon dioxide and water. And what we're interested in, or what chemists are interested in, is in determining the number of each of these reactants that would need to be combined in order to produce a given number of each of these outputs for this reaction. So that is what is the amount x1 of propane or the amount x2 of oxygen that would combine in order to produce x3 of carbon dioxide or x4 of H2O. So we need to determine these unknown quantities x1, x2, x3, and x4. So when we're trying to balance an equation, we need to keep track of the number of atoms that are going into this reaction and the number that are coming out of this reaction. They must be the same number of atoms. So in this chemical reaction that we're considering, there are three types of atoms being considered. Carbon, hydrogen, and oxygen. So here, let's start by saying there are three atoms being considered here: carbon, hydrogen, and oxygen, C, H, and O. Now, in order to balance this chemical equation, let's think about finding a vector that would describe the number of atoms appearing in each of these reactants. So here let me say, let us construct a vector of atoms for each reactant. So our first reactant was propane, or C3H8. And I'm going to construct a vector giving me the number of carbon, hydrogen, or oxygen atoms for each reactant. So for propane, here we had, for our first atom, carbon, we had 3 carbon atoms. So the first entry of this vector will be a 3. We had a total number of 3 carbon atoms. Our second atom is hydrogen, and here we had 8 atoms of hydrogen. So my second entry of this vector will be 8. And then our third atom was oxygen. Now here there was no oxygen atom present in propane, so we have a 0 entry for that last row in our vector. So for our next reactant, oxygen, O2, we had 0 carbon atoms, 0 hydrogen atoms, and 2 oxygen atoms. For the next reactant, carbon dioxide, or CO2, we have 1 carbon atom, 0 hydrogen, and 2 oxygen. And lastly, for water, H2O, we have 0 carbon atoms, 2 hydrogen atoms, and 1 oxygen atom. All right. So in order to balance this equation, let's say these coefficients must satisfy the following equation. So we had a total of X1 propane. So we're going to take X1 times the propane vector, tracking how many atoms of each type we had in that reactant, which was 380, plus we had X2 of oxygen. So the vector for oxygen tracking the number of each atom was 002. And those combine to form, on the right-hand side of our chemical equation, we had X3 of carbon dioxide, whose vector was 102, plus X4 times our vector for water, which was 021. Or equivalently, if we move everything to one side of our equation, we have X1 times 380 plus X2 times 002 minus X3 times 102 minus X4 times 021 is equal to the 0 vector. All right. So we have a system of linear equations here. Let's move on to this next page to give ourselves a little more room. So the system of equations which is being considered here, if we simplify that vector equation that we have 3x1 plus 0x2 minus 1x3 minus 0x4 is equal to 0. We have 8x1 plus 0x2 minus 0x3 minus 2 times x4 is equal to 0. And for our third equation, we have 0x1 plus 2x2 minus 2x3 minus x4 is 0. So again, it's a homogeneous linear system. We've got 3 equations involving 4 variables. So we expect to have a free variable here. So let's see if we could solve this by expressing this as an augmented matrix. So for our first row, we have 3, 0, negative 1, 0, 0. For our second row, we have 8, 0, 0, negative 2, 0. For our third row, we've got 0, 2, negative 1, and 0. So we need to simplify here. And we see that in our first row, this lead coefficient is 3. We need to eliminate 8 below it. Now 8 is not an integer multiple of 3, so we probably don't want to introduce fractions at this stage if we can avoid it. So let's think about how else we could proceed here. So in order to try to get a 1 coefficient as that top left entry, well, there are several things I could do. And the way that I'm going to proceed is by first trying to simplify the entry in my second row for the lead entry. Now to do that, I'm going to take row 2 minus twice row 1. And let's see what that buys me. My first row will remain as 3, 0, negative 1, 0, 0. And when I perform this operation, my second row becomes 2, 0, 2, negative 2, 0. And in my third row, I'm going to leave this alone for now. I've got 0, 2, negative 2, negative 1, 0. So what this buys me is the following. My lead coefficients are now 3 and 2. So if I want to have a 1 for the leading coefficient in the first row, I could now subtract the second row from the first to get that 1 term. So in my next step, I'm going to take row 1 and subtract row 2 from it, which would give me 1, 0, negative 3, 2, and 0. And in this same step, well, I noticed that every entry in my second row is a multiple of 2. So to simplify a little bit there, I could take half of my second row. So if I take half of row 2, I have 1, 0, 1, negative 1, 0. In my third row, I'm going to leave alone for right now. I've got 0, 2, negative 2, negative 1, and 0. So now I have this lead entry of 1 in my first row, and I'm going to use that to eliminate the 1 that appears in the second row below it. So to do that, I can take row 2 minus row 1. So my first row will be 1, 0, negative 3, 2, 0. My second row is 0, 0, 4, negative 3, 0. And my third row I'm going to leave alone. I've got 0, 2, negative 2, negative 1, and 0. All right. So notice now that the leading entry in my second row appears in the third column, whereas the leading entry in my second row appears in the third row appears in the second column. So in order to move this thing towards row echelon form, I want to interchange those two rows. I need the leading entry in any row to appear in a column to the right of the leading entry in the row above it. So let me interchange rows 2 and row 3. So my first row remains 1, 0, negative 3, 2, 0. My second row is now 0, 2, negative 2, negative 1, 0. And my third row is 0, 0, 4, negative 3, 0. All right. So here I now have a leading entry of 2 for my second row, and there's zeros above and below it. So the only thing that I need to have here in this second row is that leading entry to be a 1. So at this stage, it looks like we probably can't avoid introducing some fractions to get a 1 in that leading entry of my second row. I could take half of row 2. So that gives me for my first row 1, 0, negative 3, 2, 0. My second row becomes 0, 1, negative 1, negative 1 half, 0. And in my third row, well, I have this leading coefficient of 4. I know that I want to have a lead coefficient of 1 there. So in this same step, I could take 1/4 of my third row, which would lead me to 0, 0, 1, negative 3/4, 0. So now my first two columns look exactly like what I want. I've got a 1 as the leading coefficient with zeros above and below. And then in my last row, I've got a 1 as the leading coefficient, but I need to eliminate the -3 and -1 that appear above it. So in my last step for this row reduction, to kill off the -3 in my first row, I'm going to take row 1 plus 3 times row 3, which gives me 1, 0. My 3 minus 3 becomes 0. Now multiplying my third row by 3, I have a -9/4 plus 2, which would be 8/4. So I'm left with a -1/4 and 0. All right. Now for my second row, to kill off the -1 in that third column, I can take row 2 and add row 3 to it, which gives me 0, 1, 0. And then I'm adding -1/2, which would be 2/4, and -3/4, leaving me a -5/4 and 0. And then my last row, I'm going to leave alone as 0, 0, 1, -3/4 and 0. So this is now in reduced row echelon form. We see that we have pivot columns for the first, second, and third column, and I have a fourth column with no pivot. So that variable corresponding to my fourth column, that is x4, will be a free variable, and then I can solve for the other variables in terms of it. So my first equation tells me that x1 has to equal 1/4 of x4, which is a free variable. My second row tells me that x2 is equal to 5/4 of x4, which is free. And my third row tells me that x3 is equal to 3/4 of x4, where x4 is a free variable. So because these are reactants that we're talking about, or atoms, we know that x1, x2, x3, and x4 need to be integer values. We can't have fractional values. So looking at the form that we have for x1, x2, and x3, well, we see that x4 is being multiplied by some fraction of the form something over 4. So in order to get integer values, well, we could make a choice for my free variable, x4, as something which is an integer multiple of 4. So an easy choice would be 4 itself if we want to get rid of these fractions. So give myself a little room here. If x4 is chosen to be 4, then we have x1 is equal to 1, x2 is equal to 5, and x3 is equal to 3, where x4 was taken to be 4. So we have the following chemical equation for this reaction. Let me rewrite it at the top where I've got a little more room. So I would have one reactant of this propane, so 1C3H8 plus X2, which was 5 oxygen, reacts to form X3, which was 3 carbon dioxide, plus X4, which was chosen to be 4 water, H2O. So here we have balanced our equation. Now notice one thing I made a note of here in the lecture notes. This equation would also be balanced if for each coefficient we doubled the value. So let's say that I chose x4 to be 8 instead of 4. So that would give us a equivalent balanced equation, but for most practical purposes, chemists prefer to use a balanced equation where the coefficients are the smallest possible whole numbers, or smallest integer values, in order to make that reaction equation a little easier to work with.